Hello guys and welcome back to the channel. We are doing the problem of the day for today, which is Leetcode 1780. Check if a number is a sum of powers of 3. So let's have a look at what the problem statement says. Given an integer n, 12, can be 91, can be 21. What we have to do is return true if it is possible to represent this number as the sum of distinct powers of 3. And this is very important actually, distinct powers, because if you think about it, if this word, if distinct wasn't present, then it's actually possible to represent any number in the world as 3 to the power 0 plus 3 to the power 0 infinite number of times, right? 1 plus 1. So it's that way it's possible to represent every other number in the world. That's why they're saying distinct powers of 3. You cannot use the same power more than one time, otherwise return false. An integer y is the power of 3 if there exists an integer x such that y equals 3 to the power x. So the very simple approach, the very first approach which came to my mind was a greedy one, right? So for example, if I'm given the integer 12, what I will do is I will find the power of 3, which is the, you can say, the biggest power of 3, which is smaller than or equal to this n, right? So 3 to the power 1 is 3, 3 to the power 2 is 9, 3 to the power 3 is actually 27. Now I can't subtract 27 from 12, but what I can do is I can subtract this. So when I do that, what I've essentially done is I've consumed 3 to the power 2, right? I can't use this number again. It goes without saying I won't have to use any number which is greater than 2 as well. So the only options which are left with me right now are 1 and 0. Now then when I use 3 to the power 1, I'll subtract 3 from this 3 and I'll get a 0. So that's why we are returning true, because it's possible to represent 12 as the sum of 3 to the power 2 plus 3 to the power 1, right? A very simple greedy approach. Same thing I've done over here as well. The biggest power of 3, which is smaller than or equal to n, is actually 3 to the power 4. So 4 is something which I have consumed. The only options left for with me are these four things, right? Over here I see that it's 3 to the power 2 which I am subtracting, so I consume 2 and then I consume 3 to the power 0. So I can very clearly say that 91 is the sum of 3 to the power 4 plus 3 to the power 2 plus 3 to the power 0. But when it comes to 21, you can very clearly observe, so first of all you're going to consume 3 to the power 2, right? But then when it's 12, the sad thing right now is you are only left with 1 and 0, right? You cannot subtract 9 from 12 again. So if you subtract 3 from 12, you'll get a 9. So you have consumed 1. And then let's say you subtract 1 from 9, you'll be left with 8, which is greater than 0, right? So you can't actually represent 21 as the sum of distinct powers of 3. This is actually the game, and this is exactly what I've implemented in my code as well. What I do first of all is this. I find the biggest power of 3 such that it's either less than or equal to n, right? And I sort of save that number. For example, in this case that number was 2, in this case that number was 3. So I sort of save that number, right? You save that number, whatever that number is, you save it. And then what I do is I iterate downwards. What does that mean? Iterating downwards, exactly what I've drawn over here. I check the possibilities. So alright, I've consumed 4. Can I consume 3? No, I cannot. Why? Because when you subtract 81 from 91, you are left with 10, and you cannot subtract 27 from 10, right? So this is not usable. But can you subtract 3 to the power 2? Yes, you can. So let's do that. Then you are left with 1. Can you subtract 3 to the power 1 from this? No, you cannot. But can you subtract 3 to the power 0 from this? Yes, you can. And ultimately the good thing is you're left with 0. So if you are left with 0 at the end, you return true. Doesn't matter how many powers you consume. If you're left with a 0, return true then and there, right? So these are the only two steps which you need to do. The only two steps which you need to do, right? The way I have implemented it is are the same number of steps. So I I started with the value of I equals 0, and I kept incrementing I. So let's actually have a dry run. Let's have a dry run of this particular code against the second test case, n equals 91. So first of all, my I is 0. I'm actually checking at which point the power actually crosses this particular number. So initially I have 3 to the power 0. It's obviously less than equals to n. 3 to the power 1 is also less than equals to n. 3 to the power 2, 3 to the power 3, then I have 3 to the power 4. 3 to the power 4 in fact is also less than equals to n. The bad thing is it's going to increment the I. So it's going to make it 3 to the power 5, and that's when my while loop is going to break. But I cannot subtract 3 to the power 5 from 91, and for that reason I have to increment I minus minus, or the good thing I just realized was doing this I plus 1 over here, right? This is actually much better rather than decrementing the I. So I'll have this. I'll have the value of I as 4 at the end of this while loop, right? Then what I do is I subtract, what is 3 to the power 4? It's 81, right? I subtract 81 from n. When you do that, you get 10. So now 10 is the number which I am playing with, right? 10 is the number which I am playing with. So let me erase all these comments actually. Right, I'm left with 10. What I'll do is I'll obviously decrement the I, because right now why I'm decrementing the I is 4 is consumed. Okay, well and good. Now the only numbers which I'm left with are 3, 2, 1 and 0. Okay, so I'll start with 3. I will see if 3 to the power 3 is less than equals to n. What is my n right now? My n is 10. And 27 is not less than equals to n. So I'll do nothing. I'll subtract nothing. I'll just decrement the I. I check 2. Is 3 to the power 2 less than equals to n? Yes, it very clearly is. What I'll do in that case is I'll subtract 3 to the power 2 from n. Gives me 1. Right. Again, I'll decrement the I. I'll check 3 to the power 1. Is it less than n? No. My current value of n is this. Mind. My current value of n is 1. No. Then I checked 3 to the power 0. If this is less than equal to n, yes it is. So I subtract it. And in the end I get this 0, and that's exactly what I'm checking in my return statement. If n has become 0, then that means it was possible for that particular number, whatever that number originally was, it's possible to express it as a sum of distinct powers of 3. If n is not 0, it's not. So if we submit this code, let's see if it passes all the test cases. And it does, right? So as simple as that, a simple greedy approach which can very easily simulate, which can very easily understand, right? And if we talk about the time complexity of this code, then if you see the constraints, n at the very worst, it's going to be 10 to the power 7. So 10 to the power 7 is this is what, 10 to the power 1, 2, 3, 4, 5, 6, 7. So again, thing is, this is better than O of n. Why? Because you are this is like you're incrementing the numbers exponentially, right? You're incrementing the numbers in the powers of 3. So you're very easily going to reach, even if the number is this large, you're very easily going to reach. Why? Because you're incrementing the numbers like this: 3, 9, 1, 3, 9, 27, and then actually 27 into 3 and 3, and so on and so forth. So it's very easily acceptable in this sort of a constraint, and then you can very clearly see that we are not taking up any extra space, so the space complexity will be O of 1, right? I hope this video was helpful for you, and I will see you in the next one. Till then, take care.